Welcome to the second lesson in this tutorial series where we'll be creating a Minecraft clone in JavaScript. I'll be showing you how to use instance meshes to render thousands of objects on the screen at once, with the end goal being this procedural world that you can shape and sculpt right from the browser. So without further ado, let's get coding. So if you can locate the world file here, let's open that up and let's first change the size that we're passing in. So this is going to be changed to an object. So let's do default width is going to be 32 blocks and the height will be 16 blocks. And then we need to add a third dimension in here. So we're just iterating over the X and Z axes, but we need to iterate over the Y axis as well. So I'm going to add another for loop in here. And we want to look at the height here. And X and Z, those will also need to change to size.width. So now that we have this Y parameter here, we're going to pass it in when we're setting the position of our blocks. So we'll just save that. And now if we go back to the browser, we can see that we have this 3D kind of world here. We've added that Y dimension to the world. Now, as you might have noticed already, there's a little bit of stuttering when we're rotating this around. So I'm going to go and make the world a little bit bigger here. Let's do 64 by 32, and we'll save that. Now, if I try and rotate this, you can see that everything is just coming to a grinding halt. And this is because we're using a very naive way of rendering these blocks, basically creating one mesh for each block in here. And 64 by 32, I can't do that in my head, but that's a lot of blocks. And each of those draw calls is just being performed really inefficiently. So we need a way of batching all those draw calls together so we can reuse the same geometry and materials across all of those cubes. And that's a technique called instancing. So I'm not going to get too much into like the nitty-gritty details of how instancing works at the GPU level. But I did pull up the documentation for the Three.js instance mesh class. So just reading the description here, you can see that we use the instance mesh if we have a large number of objects with the same geometry and material, but different world transformations. That could be different positions, different scales, different rotations. So this reduces the number of draw calls and then improves the rendering performance of our application. Minecraft is a perfect application for this because we're just drawing a bunch of blocks. It's all the same geometry. The materials vary a little bit, and that'll add some challenges in later. But for now, we can use this and speed up performance drastically. So just pulling up one of the Three.js demos right now, this is the instancing performance demo. It can give you a really quick idea of what instancing can do in terms of increasing performance. So we have our frame rate counter up here. We're getting 120 frames per second. So if I just switch over to the naive method, and let's do 10,000 of these objects. So I'm hitting 35 frames per second right now, which is not great. You can see there's a little bit of stuttering. If I go to instance, it just moves right up to 120 frames per second. It's super fast, and you can see there's also reduction in GPU draw calls and GPU memory as well. So with instancing, it's just one draw call because these are all the same object with the same material, using 173 kilobytes of memory. If we go to naive, looks like it's still using the same memory, but it's 10,000 draw calls. So before we get into adding instancing to our project, we need a way of measuring the improvement. And we do that by having that frames per second counter in the upper left. So we're going to quickly add that in. So the frame rate counter actually comes pre-packaged with Three.js. So all we need to do is import stats from 3 examples, JSM, libs, stats.module.js. Now adding the stats to our application is super simple. All we need to do is to create a new constant here called stats, and will be new stats. And then we need to add that to our document. So do document.body, append stats.dom. This should be stats, not status. And then all we need to do is we need to update the frame rate statistics each frame. So let's go down to the animate function, and we'll do stats.update. Now, if we go back to our game here, you can see that we're getting a whopping 3 frames per second. So definitely some room for improvement there, because this is basically unplayable at this point. So now that we know where we're starting from, we can go ahead and add instancing to our application, and you can get an idea of the performance improvements that we'll get. So going back into our code now, we're going to go into our world file, and we're going to update this generate method here. So let's start by removing the old mesh here, and then we're going to create a new mesh. This will be new 3.instanced mesh. So here, this is very similar to a mesh. We pass in the geometry, we pass in the material, but there's one more argument here, and this is the maximum number of instances of the mesh that we'll have. This is one caveat with the instance mesh. You need to know ahead of time the maximum number of instances. You cannot allocate more without creating a new instance mesh. The maximum number of blocks that we'll need, so we'll call that max count. That will be this.size.width times this.size.width times this.size.height. So it's just the width squared times the height gives us the total number of blocks. So we can then pass that into our instantiation of our instance mesh here. And then we're actually going to start by setting count equal to 0. So count is the current number of instances that we have. So there's 2 different variables we got to keep track of here. The maximum count, and we have to make sure that we never run over that limit, and then also the current count. So you can render less than the maximum count, but you just cannot render more than that. Now let's go ahead and go about adding our instances here. So I'm just going to delete this old code. So what we need to do is we need to define a matrix. And this will be a 4x4 matrix, which will store the position of each block. And then we'll do matrix.setPosition, and we'll pass in the x, the y, and the z position. Now I'm also going to be adding a 0.5 offset to each coordinate here. And the reason for this is the default box geometry in Three.js. The center of the box is at the origin. And just to keep things kind of cleaner, I want the lower left corner of our world to correspond to the lower left corner of that first box. Now we need to set the matrix for each instance. So we'll do mesh set matrix at, and we'll do mesh.count ++, and then we'll set the matrix. So how this is going to work is we start with 0 instances. So then we set the matrix for the instance at index 0 to the matrix. And then this is going to increment that mesh count. So the next time we do this, it's going to be index of 1, set the matrix, and so forth. And by the end of this, count is going to contain the total number of instances. And then finally, we need to add the instance mesh to our world. So we'll just do this.add mesh. So there's not really a whole lot of extra work we need to do to make instancing work. It's just keeping track of the total number of instances, and then a little bit of extra work defining this matrix, setting the position, the transformation for that matrix, and then updating the transformation matrix for each instance. So if we go back to our game now, you can see that things are butter smooth. We're getting 120 frames per second. So we went from 3 frames per second to 120, which is what my monitor is maxed out at. So everything is working very nicely, and we're ready to start making our world a bit more interesting. Now, before we get into the world generation, I want to go ahead and add a UI to our Minecraft application. And this will help us a lot with debugging because we can tweak values while we're working on things and debugging things. So the UI that comes prepackaged with Three.js is called Lil GUI. So I'm on the website for that right now. And this is the complete documentation. It's very well written, very comprehensive. So I'm not going to get into everything here, but pretty much everything you can think of, you can do. You can do checkboxes, you can do buttons, text fields, number fields, sliders, drop downs. So highly recommend and looking up the documentation for Lil GUI and seeing all the things that are possible with that. So I'd like to keep all of our UI code separate. So I'm going to create a new file under scripts called UI.js. So here we're going to import the Lil GUI library. So import GUI from 3 add-ons libs lil GUI.module.min.js. And let's create a function in here called create UI, and we'll pass in our world object. So you need to start by creating the GUI object. So this will be the base object that we add all of our controls to. So let's go ahead and add a control for world.size, and we're going to add a property for the width. So how this works is we give it the object that we want to manipulate and the property on that object that we want to change. So in our world, we have a property called size, and width and height are properties on this size object. So I'm telling it, modify this object and the property on that object. And then we can also set some minimums and maximums and step values. So I want a minimum of 8, a max of 128. I want to step 1 at a time. And then we will call this width. So to do a similar exercise for the height here. And then finally, we want to be able to regenerate our world. So I'll just add a button here. So I'm giving it the world object and passing in the name of the method that I want the button to trigger. So finally, we need to call this in our main method. So let's go into main, and then right before animate, we'll do create UI, and then we'll pass in the world. Now, if we go over and look at our code, you can see that it's added the UI here. So I can change the width, so you can see that it's limiting it between those min and max values you specified. Same with the height. So if I set this to, say, 128 by 64, actually let's do something smaller, 128 by 10, and click generate. That will regenerate the world. So it looks like it's still keeping the old instances, so we need to go and tweak our world code. So when we're generating, we need to clear all of the existing child objects. So now when we go back here, I change this to 128, change this to 10. So now we have this nice UI that allows us to dynamically change our world parameters on the fly. We don't have to go back into the code, change them, have it rebuild, go back. So it saves a lot of development effort. Now, one improvement we can make, rather than having this button we have to click every time, you can automatically trigger generate every time the width or the height changes. So let's go back into the UI. We'll delete that. And we'll do GUI on change. And this will just pass in a function here. And all we'll do is world.generate. So now if we go back into our code, and I change the width, you can see that I don't even have to click a button anymore. It's automatically updating our world as we move these sliders. Now with our UI out of the way, we can now focus on creating the data model for our 3D world. So I'm going to go ahead and in our world class, define a new property at the top called data. So I've added a type declaration here using JSDoc. I'm going to be using this quite frequently in the project to help the IntelliSense with the editor and also kind of document what each of these properties are. Now you could argue you could use TypeScript for this instead, and that's perfectly valid, but I'm sticking with vanilla JavaScript for this project. So this data array is going to contain what each block is at each X, Y, and Z location. So we can say at an X of 2, Y of 3, Z of 20, that it's a grass block there. And that's going to be represented by this ID property here. And the instance ID is a reference to the actual mesh instance at that location. Now, the reason that we need to keep track of this is when we go to remove that block, we need to remove that instance from our scene. So now that we have our 3D data array defined, we're going to go ahead and split our generate function into two separate functions. So the first is going to be where we actually generate the data model for our world. So it's basically just defining what is the block type at each X, Y, and Z location. And then the second function is going to be generate meshes. So once we have that whole world data array defined, we're going to go through and for each XYZ location that has a block, we'll create a new instance for that. So we'll just call this generate meshes because that's what this code already does. We'll add two new functions called generate and another one below called generate terrain. So to start with, we're going to set each block in our world to the same block ID of 1. So I'm going to go ahead and write that code, and then I will talk through it. All right, so I've went ahead and implemented this function. Now I'm not typing everything out on the screen in some instances because I think it's just kind of boring to watch me type. But I'll try and talk through all the code line by line so I don't skip over anything. And if you want to copy from the video, feel free to pause. Otherwise, you can also go into the GitHub repository, which I've linked in the description down below. For each lesson in the series, I've created a single commit. So you can go into the commit history for the repository. You can find the commit associated with lesson 2 here, and you can see a snapshot of the code. So as you're following through with each lesson, you can kind of look at the end product for each of those lessons. So anyway, that aside, let's talk through this code. So first we're clearing our data array. So we can call this multiple times and it's always going to reset the world. Then we have a triple for loop here. So let's talk through this from inside out. So this is the object for our block here. So you can see we're setting the ID to 1 and the instance ID to null because we have not yet created our instance meshes yet. So we're building our world row by row, and we're concatenating all those rows together to build a slice, and then building all those slices together to completely define our 3D world. Now, before we go ahead and adapt our generate meshes function to the code we wrote up here, I want to go ahead and write some helper methods that we'll be using a lot. So we need to be able to get a block at a certain set of XYZ coordinates. We need to be able to set the block ID, set the block instance ID, and we want to make sure that when we're passing XYZ coordinates into these functions, that those functions are actually in bounds, so we don't get any errors when we're accessing something out of bounds. So I went ahead and defined all of those functions below our generate meshes function. So we'll talk through each of those 4 functions one by one. So for get block, we're passing in the X, Y, and Z coordinates. We're checking to see if those coordinates are in bounds. So let's quickly scroll down to the bottom here. And you can see our inbounds function. So the inbounds function also takes in X, Y, Z coordinates. And all it's doing is returning true if these coordinates are within the bounds of our data array. If they're out of bounds, then it returns false. And that just prevents us from trying to set the value of an XYZ coordinate that does not exist. So if that is in bounds, then we'll return the block data at that particular set of coordinates. And just as a reminder, the block data is the block ID, which is the type of block, so grass, dirt, stone, etc. And then the instance ID. What is the mesh instance at that particular set of coordinates? So if it's not in bounds, we'll just return null, and then we'll handle that in the calling code. Now the other 2 functions I wrote are setBlockID and setBlockInstanceID. These are very simple, just passing in XYZ coordinates and then either the ID or the instance ID. And of course, just checking to see if the coordinates are in bounds before we go about trying to access the data array at those coordinates. So that's it. Those are 4 helper functions: get block, set block ID, set block instance ID, and inbounds. So now that we have our helper methods implemented, we can go and finish up the implementation for our generate meshes function to match what we've done here with generate terrain. So we'll start by getting the block ID for this particular set of X, Y, and Z coordinates. So we'll do a new constant here, block ID, and we'll do get block, pass in the X, Y, and Z, and then we want the ID. So we'll define a new constant for our instance ID, and this will be mesh.count. Now we don't want to just increment this right away because block ID might be 0. There might not be a block here. So we don't want to just assume that we're going to be using this instance ID quite yet. So we'll do a check here. If block ID is not equal to 0, then we will create an instance at this location. So we're going to keep these two lines here. We're still going to set the position on our matrix and then set the matrix for that particular instance. This will now be instance ID. And then now that we've created that instance, we need to update our block with that instance ID. So do this dot set block instance ID XYZ and pass in the instance ID here. And then finally, we need to increment the count on our mesh so we can get the next available instance. So we'll do that right here. Now everything should be exactly the same as what we had it before, but now we have successfully separated out our world data from the 3D representation of the world. So we can do whatever we want with this world data. We can manipulate it in any way that we want, and we can save it to disk and not have to worry about carrying all that mesh data with it. So let's just go verify that everything is working in the browser, and it is. So this is exactly what we had before, but now we have a much more flexible system. So let's make this a bit more fun now. Let's actually get into some procedural generation. So we'll start with something simple, and then we'll work our way up to something a bit more advanced and actually useful. So I'm going to define a new property on our world called threshold, and it's going to give that a value of 0.5. We're eventually going to delete this, so I'm not going to put any comment on that. But let's go down to generate terrain, and we'll say math.random. So this will generate a random number between 0 and 1. If that is greater than the threshold, then let's set the block ID to 1. Otherwise, we'll set the block ID to 0. So this basically, what this does is randomly pick if there's a block at a location or not. And we set threshold to 0.5, so there's a 50-50 chance there. So if we go and look at our world now, you can see that a lot of the blocks are missing, and it gives kind of this Borg, I don't know if you guys are into Star Trek or not, but this Borg effect, which is pretty cool. So let's add a parameter to our UI so we can tweak that threshold value in real time. So in UI, let's add a new line here. So on world, we want to manipulate threshold, and that will just be between 0 and 1. Call that noise. So now if we go back to our game here, I can toggle this threshold value. So if I set this to 0, math.random is always greater than 0, so we can see that everything's filled in. And if I increase this to 1, you can see that slowly all the blocks go away. It's going to make a very sparse world here. Now, this is cool, but it's not useful because the noise isn't structured. It's just completely random. What we want is smooth noise. We want the noise values to change slowly over time so we can create effects like hills and valleys and things like that. And that's where simplex noise comes into play. So I went ahead and Googled simplex noise just so I can get an idea of what it looks like before we start implementing it. So I can see some examples here. So in this image on the right, we can see it looks like noise, but it's very smoothed out, very blurry. So this is going to give us kind of those rolling hills that we're looking for. And you can tune the scale of the noise to control sort of how big or how small those noise features are. So since Three.js is open source, we can actually go in the Three.js GitHub and look at the code they have. And they already have an implementation of simplex noise, which is super nice. We don't have to go and implement that ourselves or import some npm package. And that's one thing I really love about Three.js is usually if you need something, someone has already added it, either in the examples or the add-ons. The difficulty is just finding if a thing exists or not, because a lot of this stuff is not documented. All right, so that's enough background. Let's get into actually implementing simplex noise in this project. So let's delete this threshold property that we added here. And then we need to go ahead and import the simplex noise module. So I'm just going to copy paste that in here. So that's located under 3 examples, JSM, math, simplex noise. And let's go ahead and first define some parameters for our terrain generation. So I'm just going to call this params, and this is really going to be all of the defining attributes for our terrain. So if we were to use all of these same parameters again, we would get the same world out. So it's going to contain the seed value and all of the different parameters used for our noise models. So under params, I'm going to create a separate property for terrain. This is going to contain the scale, the magnitude, and the offset. So I've set these to some default values, but this will be the scale or the size of our smoothed simplex noise. The magnitude will control kind of the size of the hills, and offset is just an offset we apply to the random number that's generated. That will kind of lift everything up or down all at once. And we'll be expanding a lot more parameters on this as we go on and implement other things like water and resources, but this is what we're going to start with. So scrolling down now to our generation code, we're going to repurpose generate terrain to an initialization function. So rather than doing a random ID here, we'll just initialize every block to 0 with no instance ID. So this will be initializing the world terrain data, and we'll call it initialize terrain. And then below here, we'll add a new function called generate terrain. All right, so let's get to generating our terrain. First, we need a simplex noise generator. So we'll do simplex, and this will be new simplex noise. Now you can see our simplex noise has one argument in the constructor here, and this is a random number generator. So if you don't pass anything in, it defaults to math.random. And we're actually going to be creating our own random number generator later because math.random doesn't allow us to put in a seed value. So we want to be able to generate the same world every time if we put in a particular seed. So that way when we go back and load a world that we had saved, we get the same world that we were in before. So next we need to iterate over the x and the z axes of our terrain. So we basically need to figure out the height at each x and z location. So we'll start by getting a random number from our simplex noise generator. So we'll do const value is equal to simplex. And there's a bunch of options here. We're just doing 2D noise. So we'll do noise, and then we're passing x and z. Now we want to adjust these coordinates based on the parameters that we had defined above. So that'll be the scale, the magnitude, and the offset. So scrolling back down here, we'll put these each on separate lines. So what we do here is we scale our x and z coordinates by the scale that we define in params. So we can kind of imagine what effect scale is going to have here. If scale is set to 1, then the noise is just going to change quite quickly, whereas if we set scale to 100, the noise is going to change 100 times slower as we increase that x coordinate. So the larger the scale, the less the noise will change over a particular distance. And we also need to take into account the magnitude and the offset parameters. So we'll do scaled noise here, And first we'll add in that offset. And then we'll do our magnitude and then multiply that by our noise value. So from that scaled noise, we can compute the height. So we'll do let height equals this dot size dot height times scaled noise. And then we need to clamp that height so it doesn't exceed the minimum and the maximum of our world height. So do height is equal to math.max 0, math.min height, and this dot size dot height. So this little expression here will clamp our height between 0 and the maximum height. So we'll do another for loop here. We'll iterate over y. So if y is less than or equal to height, and then we will set the block ID at this set of x, y, z coordinates, and we'll set the block ID to 1. So to make a few quick adjustments here, we actually want to scale this between this dot size dot height minus 1 because we're starting at 0 here. And then we want our height to be an integer value. So we will floor this right here. Right, so there we have our kind of simple terrain generation code that uses simplex noise to set the height at a particular x and z coordinates. So let's go into our UI code now. And let's just delete threshold here. That doesn't exist anymore. And let's see if our world is actually working. And we can see that it is. We have some terrain being generated. So let's go and add some controls to our UI for the scale, magnitude, and offset. So in order to organize our UI controls a bit more, we can actually create folders that are collapsible. So we can put all of our terrain parameters into a single folder, which I'm going to do that now. So create a new terrain folder. That will be GUI, add folder, and then we'll just pass in terrain as the label for that folder. Now I'm going to go ahead and add the 3 UI controls to control our noise parameters. So similar to how we added controls to the GUI, we can add controls right to the folder. Then we're controlling the scale, the magnitude, and the offset. So now if we go back here, as I tweak these values, you can see this is changing over time. So with a very high scale, everything's very smoothed out. With a small scale, we get very jagged terrain. And you may notice that our world is changing completely every time we change the scale. And this is that issue with math.random I talked about before. We're not using the same seed value every time. So it's completely generating a random world. So quickly just tweak magnitude here, make sure that works. So when that's set really low, we get these flat hills. If we make it really high, we get these big cliffs. And then we can change the offset to kind of move everything up and down. All right, so our terrain generation is working perfectly. So I think we should go back and implement that random number generator that allows us to pass in a seed. And I think after we implement that, you'll see what effect that has here when we start changing these properties. So just very quickly looking back at the source code for simplex noise, if we look at the comments here, you can see that R by default is set to math. And the comment here is pretty helpful. You can pass in a random number generator object if you like. It is assumed to have a random method. So that's what we're going to do. We're going to create a new random number generator class that's going to have a random method on it. And we're going to set that up so when we pass in a seed value, random will always return the same sequence of random numbers. So back in our code, under scripts, let's create a new file called rng.js. So this code is very obscure. I just actually copied it from Stack Overflow. I'm not going to get into how this works. I actually don't know how this works. I just know that it works, so we're going to roll with that. But you can see that I'm passing in a seed value here. So every time I'm creating this new RNG class, I pass in that seed, and then every time I call random, I'm always going to get the same sequence of random numbers. So every time I'm generating a world with that seed, I'm going to get the same result. So let's go back into world, and let's import our new random number generator. sudo import RNG. And then let's go down to where we're defining our simplex noise function. So create a new RNG here. So let's scroll up here and let's add a new parameter for our seed. So we'll just default to a seed of 0. And then we'll pass that seed into RNG. And then finally, we'll pass in RNG to the simplex noise constructor. And of course, we also need to update our UI as well. So we'll add a new property at the top here. And this will be seed, and we'll just cap this between 1 and 10,000. All right, let's go back to our game here, and you can see now that as I change seed, it's just changing the seed for that random number generator, and we get a different world each time. But now as I change scale, you can see that it's keeping the same world, it's just changing the features of that world. It's not completely regenerating a whole new random world. So it's kind of fun to watch as we stretch and shrink this. We can see the hills kind of coming together and expanding. We can lower the magnitude, increase it, bump the offset up and down. So now we have a nice tunable world. All right, so let's wrap up this video by adding some additional block types. Right now we just have this grass block and it's not very interesting. So I'm on the Minecraft wiki right now, and you can see that there's actually a whole ton of blocks that we could add here. So I think for our purposes today, we're just going to focus on adding in grass and dirt. So just getting those two different block types, and we can expand from there. So let's go ahead and create one more file here under scripts. We'll call this blocks.js. And this is going to be a file where we define all of our block types and the metadata that is associated with those blocks. So let's create a new constant called blocks. And then we're going to name our blocks here. So we're going to have an empty block. We're going to have a grass block. And then we'll also have a dirt block. The ID for empty is going to be 0, ID for grass will be 1, and ID for dirt will be 2. So let's also add some names for these. So name, we'll just call that empty. This will just help with debugging later on. This will be grass, and this will be dirt. And then we need to set the colors for each of these blocks. So empty, of course, has no color, so we won't define a color there. But for grass, we'll do 559020, which is a reasonable color of green. And then for dirt, we'll do brown. This will be 8070 and 20. So this is a very simple just object containing our block definitions. We'll definitely be expanding on this later as we add in more block types. So going back to our world file, let's import blocks. And then let's start adding some additional block types here in our mesh generation. First things first, I want to, in our initialize terrain function, we're using this literal 0 here. I'd rather use the ID for empty. So this is just a bit easier to read, so you know that we're initializing our blocks to empty here. Now what I would like to do is for all of the blocks on the surface, so the very top blocks, I want those to be grass, and then everything below that is going to be dirt. So let's go back to our generate terrain function where we're setting the block ID, and we're going to change this code here. So we're actually going to iterate over the entire height here. So this .size.height. So if y is less than height, then we'll set the block ID to dirt. Otherwise, if y is equal to height, then we'll set that block ID to grass. And then Otherwise, we'll set the block ID to empty. So everything below the height is dirt, everything at height is grass, everything else above that is going to be empty. So now that we've updated our block IDs, we need to update our mesh generation. So how do we set the color here? First thing we need to do is to go find our material at the top. We're already setting this to green. Let's just clear that out. So if we were to look at our world now, we would see that everything is white as expected. So going down back to our generate meshes function, there is actually a property on the Three.js instance mesh where we can set the color. So the default shader allows you to change the color per instance without creating a completely new instance mesh, which is pretty nice. So below where we're setting our matrix, we'll do mesh, and we'll do set color at, pass in the instance ID, and we'll do new 3 color, and then we need a color to pass in here. So we'll get the block type, and this will just be getting all the values of blocks, and we'll find the block where the ID is equal to our block ID. So how that works is we're just getting an array of all these objects here, and we're finding the one where the ID of the block matches the block ID at this particular set of XYZ coordinates. Perhaps not the most efficient way of representing this because we need to do a find each time, but this code runs pretty fast, so we can always change it later to be more efficient. So now that we have our block type in the constructor for 3.color, we can do block type dot color, and that allows us to pass in that color. So now if we go back to our game now, we can see that all of the blocks on the top are this shade of darker green that we have, and then everything below that is dirt. It's a brown color. And everything above that is empty, so there's no block there, and that's also what we wanted. So now we can kind of tweak all of this, change our world size, and it's actually starting to look like a real Minecraft game now. So the last issue with our code here that we're going to address is we are rendering all of the blocks even if they're hidden. So as I zoom in here, it's really hard to see with this, but you can see that there's all these little blocks inside the hill. We're rendering all of those instances even though the player can't see them. So we need to change that because that's going to kill our performance later on. So at the very bottom of our file, we're going to create a new function called isBlockObscured. So we'll pass in a set of XYZ coordinates, and then we need to basically query all the blocks above, below, to the left and the right, front and back. So if a block has blocks on all sides of it, then we know that block is hidden and we don't need to render it. So I went ahead and implemented this function here. So let's walk through what's going on. So you can see I'm getting the blocks above and below. So y plus 1, y minus 1 to the left and the right, x plus 1, x minus 1, and the blocks in the front and the back. So that'd be z plus 1, z minus 1. So I'm getting the ID of each of those blocks, and if there's no block there, then I'm just setting that block to empty. If any of these blocks is empty, then we know that the block in the center is exposed on that side, and the player can potentially see that block, so we need to render it. So in that case, is block obscured, we return false. Now, if none of the blocks are empty, then the block is completely obscured, so you return true. So let's go back up to our generate meshes function here, and let's change this line. So if block ID is not equal to blocks.empty.id and the block is not obscured, then we will go ahead and add an instance. So Let's go back to our code. Everything looks correct. Now, let me expand up the world a bit, expand the scale. Now, if I kind of zoom inside here, you can see that it's completely hollow. Whereas before, this was all filled with blocks. Now we're only rendering the blocks on the very surface of our world. All right, so that's all I plan on covering in this video. I know it was kind of a lot, but I think we have a pretty cool result here. We have this world. We can pick from one of 10,000 worlds. We can change the scale of the terrain, the magnitude of the hills, the offset, and everything is dynamically controllable from the UI, which is really nice. So in the next video, we're going to look at procedurally generating resources. So we're going to create little mineral deposits, coal deposits, iron, things like that. So we're going to create these little 3D blobs that live inside of the terrain. So that actually gives us a reason to go and mine into the terrain to get those resources. So I hope you're finding this tutorial series informative and useful and fun. If there's anything that you find confusing or you'd like me to explain a little bit more, please leave it in the comments below. And be sure to hit that subscribe button so you can be notified when the next lesson in this series comes out. So until then, take care everyone. Thanks for watching.